Integrated circuits have drastically changed the electronics industry and have become an integral part of our society.
Is it okay if I use your phone?
Okay. They are used in sophisticated electronics and computers, which are part of our everyday lives.
Hi, I'm not here now, but leave me a message and I'll get back in touch.
Hello, comma. My name is my name. I'm using head movements to move the mouse cursor around and speech to do all kinds of words and commands.
These computers are used extensively in research and development to improve the quality of our lives.
Voice console, wake up. Press button. Period. Go to sleep.
The modern electronic era bloomed when thousands of transistors and other electrical components were integrated on a small slice of crystalline material. Today's chips contain millions of transistors and are the heart of the microelectronics, communications, and computer industries. Inside a computer, there are rows of these tiny devices, each one capable of storing information or executing hundreds of millions of operations a second. Integrated circuits have evolved from bulky vacuum tubes and transistors and are fabricated in technological centers like Silicon Valley. It all begins with the growth of pure silicon crystals. Silicon is the common element found in sand. It is 28% of the Earth's crust and second only to oxygen in abundance. The silicon from the sand is refined and purified as polysilicon chunks. The purified silicon is then heated to a molten state. A small solid piece of single crystal called a seed is gently lowered into a rotating vat of molten silicon. Using the cubic atomic structure of the seed as a pattern, a new crystal will form as the symmetrical extension of the original seed. The hot liquid silicon in contact with the seed begins to cool and solidify as it is gently pulled from the molten region. The cubic atomic structure of silicon consists of atoms with 4 electrons in their outermost shell. In a perfect crystal and at low temperatures, each silicon atom bonds with its 4 neighbors. There are no free electrons to conduct current. At room temperature, however, the silicon crystal has enough thermal energy to free a small number of electrons. These free electrons conduct current, as do the holes where the electrons have been. This conductivity can be increased by adding impurities called dopants. Dopants are elements which are similar to silicon in atomic structure. There are two types of dopants. N-type dopants, like arsenic or phosphorus, have one more valence electron than silicon. P-type dopants, like boron, have one less. When some silicon atoms are replaced by arsenic or phosphorus, the crystal is called N-type, due to the extra electrons or negatively charged free carriers. If boron is used, the missing electron behaves very much like a positive carrier. The crystal is called P-type. These free electrons and holes move through the crystal, conducting electrical current in response to applied electrical fields. After 48 hours of growth, a single crystal results from the liquid melt. The ability of silicon to be either a poor or a good conductor by fine control of dopant concentration makes silicon a member of a class of materials known as semiconductors. The shiny rippled surface of the crystal is ground to form smooth, uniform ingots. A curved diamond edge blade saws the ingot into wafers that are as thin as possible without being too fragile and difficult to handle. The wafers are scrubbed and the edges are rounded off and beveled to reduce chipping. The wafers are then ground smooth on both sides to obtain a consistent flatness and thickness from wafer to wafer. They are rinsed and etched in chemicals to remove surface contamination. The final polish is done on only one side of the wafer. The characteristic mirror-like luster is free from scratches and contamination. The wafers are measured for resistivity, which is a function of dopant concentration. They are inspected, packaged, and sent to fabrication areas, where they will be made into integrated circuits. Meanwhile, teams of engineers work together to design circuits that will be fabricated on the wafer's surface. In this facility, over 100 specialists are often required to design the next generation of a microprocessor. The organization of a design team corresponds to the organization of a completed chip.
Right now our iCache is like 32K.
So let's at least offer them an option which gives them the performance.
Computer architects, working at the highest level of abstraction, define the overall function of the chip. They establish the microarchitecture, which regulates the timing and sequences of instructions that tell a microprocessor what to do. The design is divided into areas that perform specific functions. Each unit is assigned a logic designer who works at the logic level to create more detailed specifications and establish hardware needs. Each unit is further subdivided into functional blocks. Each block is assigned to a circuit designer who works at the transistor level.
Alignment shifter, and for this alignment shifter, we should be picking.
The design becomes a maze of interconnected microscopic switches, known as transistors. These transistors turn on and off hundreds of millions of times per second, and in the process, either amplify incoming electrical signals or represent this information as a digital 0 or 1. These two states make up the code used in modern electronic communications. They are the logic or language that computers understand and translate into useful operations. To see how transistors work, let's examine a pair of CMOS complementary metal oxide semiconductor transistors. The N-channel transistor has two heavily doped electron-rich N-type regions, separated by an electron-poor P-type substrate. The electron-rich regions, called the source and drain, become the ends of an electronic switch, which is normally off. The gate electrode is close to, but electrically isolated from, the P-type region. The application of a small positive voltage creates a net positive charge on the gate. This charge attracts electrons from the drain and source regions, turning the switch on. When the gate voltage returns to 0, the transistor is again off. In a normally off P-channel transistor, heavily doped P-type regions are separated by a lightly doped N-type substrate. The application of a small negative voltage repels electrons but attracts the positive carriers, turning the switch on. It is possible to fabricate both P and N-channel transistors on the same wafer by doping sections of the wafer. This is known as complementary MOS, because a gate voltage which turns a P-channel transistor on turns an N-channel transistor off. To illustrate this complementary switching, a top view shows current flowing through the P-channel transistor in the upper left. A voltage signal entering the gate electrode turns on the complementary N-channel transistor, allowing charges to drain through. This opens the lower set of P-channel transistors so the current flows through them. In this way, electrical signals can rapidly propagate through a complex maze of switches. Designing these circuits requires software and hardware tools like computer-aided design and computer-aided engineering. After circuit designers complete each block of circuitry, the computer checks for accuracy based on geometrical and electrical design rules. A mask designer takes the circuit schematic and manually lays out the channels in each layer of the mask and generates a master blueprint. These drawings are usually 400 or 500 times the actual size of the chip and enable engineers to visually check for errors.
Exactly the same class. Right. You come in, tap, and then stand.
This information is electronically fed into a computer-controlled electron beam machine. In an ultra-clean environment, a fine electron beam will etch the patterns onto a series of chrome-plated glass plates. After the glass plates are etched, they become the masks that are used to transfer the circuit patterns onto the wafer. Each mask is inspected to ensure the patterns are good. The masks undergo a final wash in acids before they are carefully packaged. The following simplified sequence shows how masks are used to build transistors step by step. The first mask creates a well of doping so that the neighboring N-type and P-type substrates exist on the same wafer. The P and N channel regions are specified and electrically isolated by the growth of silicon dioxide. Next, the gate electrodes, which turn the transistors on and off, are formed. Masks number 4 and 5 define the source and drain regions of the N-channel and P-channel transistors. The next mask defines the contact holes, which will enable the aluminum wiring used to interconnect the individual transistors to contact the source, drain, and gate region of each transistor. Most integrated circuits use from 12 to 25 masks, depending on the complexity of the circuit and the type of process. And now, let's go into a research laboratory and follow a very simplified version of a CMOS fabrication process. From start to finish, a complex process may involve hundreds of individual operations and may take a number of weeks to complete. To have a successful run, control of contamination is extremely important. It takes just a few microscopic dust particles to drastically reduce the yield of effective semiconductor devices. The equipment, gases, and chemicals that come in contact with the silicon wafers must also be of the highest purity and free of contamination. To start CMOS fabrication, P-type wafers with a specific resistance are selected. All types of integrated circuits, including CMOS, are fabricated using 4 basic techniques. Formation of thin layers of silicon dioxide, introduction of dopant atoms, deposition of a variety of insulating and conductive materials, and precision patterning of each of these layers. Before the process begins, the laser-scribed identification number of each wafer is recorded. We start by cleaning the wafers in hot acids. Hydrochloric acid, sulfuric acid, hydrogen peroxide, ammonium hydroxide. That's what it takes to remove all the organic and metal contaminants. This cleaning procedure is repeated throughout the process to make sure the surface of the wafers stay absolutely clean. The wafers are rinsed in deionized water and spun dry in filtered nitrogen gas. In a vertical furnace, high temperatures will be used to grow a layer of silicon dioxide. Silicon dioxide is a glass-like insulator which protects the silicon substrate beneath it from unwanted reactions. Pure oxygen reacts with the silicon surface in a hot furnace to grow a thin layer of silicon dioxide. This process is similar to the way the sun's heat and the air's oxygen turn the shiny new paint job of a car to a dull coat over the years. The silicon dioxide layer will be etched and used as a stencil to dope specific regions of the wafer. But first, the pattern for the stencil is applied to the silicon dioxide through a photographic technique called photolithography. The first mask pattern will be transferred onto the wafer using photoresist, a material which is sensitive to light. In slow motion, we can see the thick photoresist, which is a resin dissolved in solvents, evenly spread over the surface. The wafers transfer to heating plates and bake at low temperatures to evaporate the solvents, leaving a thin layer of resist. The wafer then enters a computer-controlled machine called a stepper. Inside, the wafer is positioned underneath the selected mask pattern. Ultraviolet light exposes the pattern across the surface of the wafer. In this way, many chips are made on a single wafer. By increasing the diameter of the original crystal, larger wafers are sliced and more chips can be made on each wafer. The wafers are then developed. There are two types of photoresist, negative and positive. A negative resist hardens when exposed to light and remains on the wafer when developed. In this run, a positive resist is used. When exposed to light, the resist changes chemically and is removed when developed. The regions of silicon dioxide, now unprotected by photoresist, are then etched. Although acids can be used for etching, most wet chemicals etch in all directions at equal rates, which can result in undercutting of the photoresist. Undercutting could create an inexact transfer of the mask. When a critical fine etch is needed, the wafers undergo a dry etching process called plasma etching. In the plasma chamber, a chemically reactive gas provides free fluorine atoms, which react with the exposed silicon dioxide to leave sharp vertical walls. High magnification SEM photographs show the precision of these etched regions. The hardened resist is then removed in a dry process using oxygen plasma, which may include fluorine, followed by hot acid baths. This leaves a stenciled silicon dioxide layer as insulation. Photolithography will be used with each of the subsequent masks in the process. This technique allows us to isolate microscopic regions of the wafer and construct them into components of the electronic circuit. In this way, the transistors and circuits are gradually built, a layer at a time. In the ion implanter, dopant ions will bombard the wafers to create N-type regions. The depth of the ion implantation depends on the amount of energy used. Dopant ions are separated from other elements and accelerated to high velocities in a strong electric field. The ions are then driven into the wafers, implanting the exposed silicon regions. The silicon dioxide layer on the wafer blocks the dopants from unwanted regions. Because these wafers are P-type, phosphorus ions, which are N-type dopants, are implanted. Exposing the wafers to high temperatures diffuses the ions deep into the silicon substrate. This creates a well of N-type substrate where the P-channel transistor will be built. If the wafers were N-type, then boron would have been implanted to create P-wells. A new thinner layer of silicon dioxide is regrown, and its thickness is carefully monitored and measured. In a deposition furnace, a layer of silicon nitride is deposited over the oxide layer. The nitride layer prevents additional growth of the silicon dioxide layer and protects the region where the transistors will be built. Photoresist is again evenly spread on the wafer and baked in preparation for the next mask. Using a computerized machine, each new mask is perfectly aligned to the pattern already on the wafer. The second mask, used to define the actual transistor regions, is also exposed across the surface of the wafer. The wafers are developed to remove the exposed photoresist, then rinsed and baked. The wafers are then plasma etched. The free fluorine atoms react with the exposed nitride. After the photoresist is removed, the wafers go back into the oxidation furnace. A thick insulating layer of silicon dioxide, known as field oxide, will be grown where the nitride has been etched. To grow these thick layers of oxide, oxygen combined with hydrogen is introduced on the wafers as steam. This insulation reduces the electric fields between the surface and the underlying regions. Through the microscope, the field oxide looks like white boundaries. It will block the current from leaking between devices, allowing thousands of transistors to coexist in a small area. The remaining nitride layer is then removed by a combination of dry and wet etching. The wafers are then implanted with boron ions, which penetrate the silicon substrate only through the thin oxide layer. This provides uniform electrical characteristics in the regions where the transistors will be built. This thin oxide, which may have been damaged by the implantation process, is removed, and a new layer of silicon dioxide is grown in the gate area. In the vertical furnace, the gate electrodes will be formed by depositing polysilicon. Polysilicon consists of many small grains of silicon, which will be doped with phosphorus, an N-type dopant, to make them more conductive. With photolithography and the next mask, the polysilicon layer will be etched to create the gate electrodes that turn transistors on or off. To carefully control this etch step, the polysilicon is dry etched. The width of these gates determine the distance that separates the source from the drain of the transistor, and ultimately the speed of the circuit. The remaining photoresist is removed once again. The gates become the first conductive layer connecting to different transistors. Mask number 4 allows the implantation of the N-channel regions with a high concentration of N-type dopants to form the highly conductive source and drain regions of the N-channel transistors. Mask number 5 uncovers regions in the P-channel transistor, which are implanted with a high concentration of boron, a P-type dopant, to create the source and drain regions of the transistor. The photoresist is stripped, and again, the wafers are cleaned. In a furnace, the wafers are annealed, and defects created by ion implantation are repaired. Next, a thick insulating glass layer is deposited. The many different layers previously deposited and patterned are completely covered, leaving an unleveled glass surface with varying depths of fields. To ensure every part of subsequent mask patterns are transferred in sharp focus, the surface must be planarized. A chemical-mechanical method is used to polish down the thick oxide layer on the wafer surface. This creates the flat, level surface required for producing high-resolution patterns. Photolithography and mask number 6 define the openings through which the metal wiring will be able to contact the source, gate, and drain regions of each transistor. By plasma etching the unmasked portions of the silicon dioxide, contact holes are created. Through the microscope, these holes are seen as the small dots. In most chips, these contact holes are so small, they must first be filled with a metal plug to ensure a solid electrical connection. Tungsten metal is deposited over the surface to completely fill these tiny holes. In a metal etcher, the top tungsten layer is then etched or polished down to the oxide layer. This leaves tungsten plugs in the contact holes, connecting to the polysilicon gate and the source and drain. A layer of an aluminum silicon alloy is deposited onto the wafer to become the first level of circuit wiring. Mask number 7 patterns the aluminum. This is the first level in which individual transistors are wired together to form complex blocks of circuitry. The excess aluminum is removed using dry etching, and the photoresist is removed. This leaves narrow metal strips which extend from one transistor to another and form the first layer of wires connecting the circuitry. In sophisticated circuits, the wiring is so complex that it is impossible to complete with a single level of aluminum wiring. Several additional layers of wiring are often produced on the same circuit. This SEM photograph shows a device with 2 metal layers. This cross-section shows 5 metal layers. Each additional layer typically requires at least 2 additional masks and the following process steps. Deposition of silicon dioxide to electrically insulate one layer of wiring from the subsequent levels. Photolithography, masking, and etching to open contact holes between the top layer of metal and the next layer to be deposited. Deposition into the contact holes of another tungsten plug. This ensures a good electrical connection between wiring levels and a more planar surface. Deposition and patterning of the new upper level of aluminum alloy. After all of the desired levels of metal interconnects are in place, a final layer of silicon nitride is deposited to protect the fragile aluminum interconnects. In the last photolithography step, only the nitride on top of the bonding pads is etched away. The white aluminum pads are all along the outer edges of this chip. They are the contact points between the wires from the outside world and the integrated circuit. The wafers are then stripped to photoresist, and the run is complete. Finally, the wafers are ready for electrical testing and packaging. And me, I'm ready for my own kind of run.